Okay, so good evening, everyone. So I hope I'm audible. You can let me know. Just let me just cross check also. Okay, I think it's okay. Okay, done. Okay, so let's start today's session. As you know, we'll be discussing some of the questions for PSUs, particularly as you know, we are focusing more on as of now on HAL. Okay, so today's session is for the machine design, as has been shared with you. The details has been shared with you. So let's go ahead with some of the areas which I will be covering in today's session from the machine design portion. Okay, so you know you already have this schedule that we have given. So I think today on 9th March, that is, I am having the live schedule. Okay, so let's go ahead with this. Okay, so we'll discuss one by one these questions, but it will be advisable that if you respond while we are discussing these questions, so it is going to be then interactive section. Okay, so we should keep it interactive. So let's go ahead with this particular question. Just go through this question and try to answer. Okay. So some of the questions I will be taking from gears, from design portion, and then some of them may be from this what do we call clutch also at the end, and some of the questions are going to be from bearings. I think these are the three broader areas that we are going to cover today in this particular, and shaft design also. Okay, so these are the areas which will be covered in today's session. So as you go through, when both pinion and gear are made up of same material, then from design point of view, which one of these statements are correct that you have to answer. So you have to decide based upon the beam strength equation. You know, so you already know the beam strength of the gear tooth is given by, right? You're giving A, D also. Beam strength, how do you know? You give it by sigma B allowable into pi y BM, BM into pi y, right? This is the beam strength of the gear tooth. It means this is the tangential tooth load. Beam strength is what? This is the maximum tangential tooth load that your gear tooth can carry. This is the same as beam strength. So it will depend upon these factors. So you know this is the allowable value of the bending stress. So allowable value of bending stress, it means this is a property of the material. So this is the fixed value. What about the width of the gear tooth? Obviously, whether it is a gear or pinion, for both of them. So provided he is talking about the pinion and gear are made of same material. So when pinion and gear are made up of same material, then allowable value of the bending stress will be same. What about the width of the gear tooth or pinion tooth? It has to be same for both of them. So this is also same. What about the module? Module of any two gears mating with each other has to be same. If it is not same, you cannot mesh them properly, right? Width has to be same, module has to be same, and since both are made of same material, and bending stress, that is allowable value of bending stress, is going to be the property of the material. So for both of these two, this beam strength, this allowable value of bending stress is also going to be same. Pi is constant. So deciding factor, which one of these two is weak? So which out of these two, whether gear or pinion, which one of these two is going to carry lesser load? This is basically the load value only. This is the maximum tooth load, tangential tooth load that gear set can carry, or gears or gear and pinion can carry. So it means deciding factor is the Lewis form factor, small y. So if you have the idea of Lewis form factor, how is that value, then I think you will be able to get the answer. So I have written those values over here. Just have a look over here. So now the same equation that I have written over here, deciding factor is y. Y will decide whether the beam strength of that gear tooth will be less or more. So for example, this is the Lewis form factor, that these values you need to remember. He can directly frame the question from here. So these values you should have in mind. So for different pressure angles, you're having these values. Now, if you see over here, for the pinion, as you the lesser number of teeth, if you have lesser number of teeth, then this total value is going to be more. If total value is going to be more, then that means this total value is going to be less. So in which case it is going to be? In case of pinion, because in case of pinion, you are having lesser number of teeth. It means if less the number of teeth compared to gear, then obviously this total value is more. If this is more, then total value is going to be less of this Lewis form factor. So it means for the pinion, the value of the y is going to be less. It means out of the gear and pinion, it is the pinion which has the less beam strength, or which has less capacity to carry the tangential tooth load. So you already know, out of these two, we should base our design based upon what? Pinion or gear? Obviously, we say the smaller one, which is carrying the less load, which has a less capacity to carry the load. So out of these two, the less capacity, when these are made up of same material, when they are made up of same material, in that case, pinion has less capacity to carry the load, tangential tooth load, because y is small, and therefore we are going to design the gears based upon the pinion. So that is why our pinion is the determining factor, or we are going to design this gear and pinion set based upon the pinion. So had they been of different material, had the pinion and gear, they are of different material, in that case, who is going to decide which one is weaker? So basically we are going to decide the design, or we are going to make the design based upon the which one is weaker out of these two. So if, let us say, if the question is framed this way, they are made up of different materials, then what should be your answer? Then you cannot decide directly. You have to decide based upon what? When the material is different, then this value is going to be different. For pinion, it will be different. For gear, it is going to be different, because both are having different material. So it means irrespective of the material, whether material is same or different, width of the gear should be same, module should be same, pi is constant, but y again will depend upon what? Number of gear teeth. So it means the deciding factor, that is which one of these two is going to be weaker, will be the combination of sigma b allowable and y, because for gear and pinion, this is also different and this is also different. So the combination of these two will decide which one of these two is weaker, and therefore accordingly we are going to design. Whether if gear is weaker, then we will design based upon the gear. If pinion is weaker, then we will design based upon the pinion. So that is how your answer should be. But since over here the both have same material, so only deciding factor is the Lewis form factor. And one more thing you should keep in mind, this small y is also known as the Lewis form factor, and also capital Y is also known as the Lewis form factor. Only difference being that capital Y is the pi into small y. That is the only difference. So which one is the Lewis form factor? You will say this is also Lewis form factor, this is a Lewis form factor. Only difference being that if I am writing capital Y, then this value will be more compared to smaller y by a term, that is a 3.14 if you will multiply by that value. Okay, so go to this particular question. For accurately cut gears operating at velocities up to 20 meter per second, the velocity factor is equal to. Now, first of all, you need to have the idea that where we make use of the velocity factor and why we make use of that velocity factor. I think based upon that, I have framed some questions as we will be going further. So first, you need to have the idea of velocity factor, and these are the factual values. Obviously, you need to remember. So you are saying B. Okay. So this is the situation that you need to know. Anyway, you have answered it correctly, I think, Shubham. So now, this, how much, if I ask you, how much is the load which is acting on the gear tooth? You will say that is decided based upon what? Power that you are going to transmit. Okay. So, okay, good, Gagandeep. Anyway, so let's say, for example, when we talk about this, how much is the load which is acting on the gear tooth? Okay, so you will say, I will calculate it from where? Power. Power is equal to how? 2 pi n into mt divided by 60. That means if you have to calculate in watt and all that. So what is this value of the torque? Torque, we have to decide based upon the tangential tooth load which is acting over there and the radius. Let's say radius, I am writing it d by 2. So this is the tangential tooth load. I am denoting it with the PT. This means if this is the gear tooth, so over here, this is how the profile is. So along this, this is a pressure line. So this is the load which is acting over here. So this is the tangential tooth load which is acting. So it means power is decided based upon this. That means, how much power will be transmitted. This is the formula. So from this power, if you know, you are going to can find out what is the value of the tooth load which is acting on the gear tooth. Okay, good. So how much gear tooth load is acting, you can find it out from here. But you know, this calculation is simply based upon the power, right? That how much power you are transmitting. In addition to it, you are having so many other factors which will also decide that how much actual tooth load is acting. This is not the actual. For example, this is assumed based upon the ideal conditions. That if I am assuming that the gear tooth profile that I'm having over here is, let us say, perfect, right? There is no inaccuracy over there. Or also when we are mounting the gears, there is no misalignment on all other factors. That means when we are saying that theoretically, if I ignore all other factors, then this is the tooth load, the load which is acting on the gear tooth, tangential tooth load acting on the gear tooth. But practically, you know, there are a number of factors which decide that how much is the load acting. So this is always acting. But is there any other load which is also acting on the gear tooth in addition to it? Definitely it is going to act, because your gear tooth profile cannot be perfect. There could be misalignment, and because they are running, then obviously because of those misalignment errors and all those factors, there can be, while meshing, there could be some additional load acting on that particular those gear tooth. So what is that additional gear load or gear tooth load which is acting on the gear tooth? So if you can find it out, then your job is done. Then you can tell me that this is the actual load acting on the gear tooth. So it means the actual tooth load will not be same as that you have calculated from this, but will be greater than PT. So I want to find out the actual gear tooth load. So what is this value? So this, sometimes we call it as a P effective, that is effective or actual. So either you call it as a P effective or actual tooth load acting on the gear tooth. So you are having two prominent ways of finding out this actual tooth load. Either what you do is you are saying that because of inaccuracies and all other factors, some additional load will be acting. So what is that additional load? Either if you can calculate it separately, then it is okay. You are simply going to add it on this. You are having this. If you calculate that additional load, then simply add that value over here to PT. You are going to get the effective tooth load. That's what I have done over here. You see, actual tooth load that is acting on the gear tooth will be equal to the tangential tooth load that you're getting from this formula plus additional tooth load. Because of those inaccuracies and all those other factors, I'm simply adding, and you're getting the effective tooth load or actual tooth load. Now, is this incremental or additional tooth load you get from you're having one equation that you may have heard called as Buckingham's equation. So Buckingham equation gives this value of this. So this is one way of doing it. There's another way of doing the same thing. That means I want to find out the actual value. So if you can divide this tooth load by some factor which is having a value less than 1. So what is going to happen to the total tooth load? That is going to increase. So if I will either this way, or you can also do the same thing by this way. That means if you divide this tooth load by a factor which is having a value less than 1, then the total value will be more than PT, obviously. So it means this will become the actual tooth load. Right. So this approach was adopted by the Barth, and that is why this factor called as velocity factor or dynamic factor, and this is value was given by the Barth first time. And what are those values? They have been mentioned over here. So for you, important is the meaning of effective. What is the meaning of PT? What is the meaning of P effective, the actual tooth load, and how actual tooth load I can calculate? Either I can calculate from this, or I can calculate this way. If this is the way, then I should know how to find out the value of this velocity factor. We call it as a velocity factor or dynamic factor. So these are some of the values that you need to remember for different conditions. This value depends not only on the velocity, but also the time of this type of manufacturing process or the way it has been manufactured. For example, if you see, if they are the normal gears, commercial cut gears for velocity less than 10 meters per second, then you use this way, you calculate this value this way. And if this is accurately and hobbed, this process is this way, then this will, for the velocities less than this, you use this method. And if this is the method of manufacturing, then in that case, and having a velocity greater than 20, then you can go ahead with this and find out the value of kV. But all these values are going to be less than 1. Keep it in mind, if this kV value will be less than 1, only then you can say this total value will increase. Otherwise, if it is greater than 1, then you're going to have the value what? If it is greater than, if this is greater than 1, then actual value will reduce. It means there is some kind of understanding gap, or you are having some kind of, you can say, wrong information available with you. He can also give the same information. Okay, so now let me just first come over here. So based upon this formula, you can directly go to this. He has given you very accurately over here, accurately cut gears, hobbed and hobbed, velocity less than 20. You are having this particular formula to calculate this. And obviously the value of the V, keep it in mind, this value of V is over here in meter per second. Clear? Okay, so let us say one more question he can frame where you may get confused. Let us say I am giving you the value of the velocity factor as 2. Let's say he has given you a velocity factor 2 and he is asking you to find out the value of the actual tooth load or P effective. Can you find out that value? Let's say he has framed question this way, that velocity factor given to you is 2. Now tell me what is the effective tooth load acting over here. So you don't have to simply just cram this formula, otherwise interpretation may be wrong. Now if it is 2, then what you will do? Okay, PT is, let us say, 100. Okay, divided by 2, 50 kilonewton, let us say, actual. If you are doing this way, then your interpretation will be wrong. Reason being, this is the PT value based upon the power. And in any case, actual value of this particular tooth load will be greater than this. But if you did this way, you're going to be wrong. So it means what he has given you, he has given you the value of 1 by kV. This means it means what he means to say, what he wanted to say over here is that actual tooth load or effective tooth load will be 2 times the value of PT. That is what he is saying. So just keep it in mind always, the actual value of the tooth load is going to be greater than the tangential tooth load that you have calculated from the equation, that is a power equation, right? Anyway, this is how you have to. Okay, just go to this particular question. Okay, what it says, the surface endurance limit. Surface endurance limit of gear material is dependent on its. Surface endurance limit of gear material is dependent on its what? Out of these two, out of all these values, it will depend upon what? When you talk about the endurance limit, that means you must get the idea some kind of fluctuating or repeated load may be acting, right? It means if that is acting, then there is a certain kind of failure that is going to be over there. It must be a fatigue failure, right? Now, in this case, in case of gears, when you are having gears coming in contact with each other, and since they are rotating, and so since they are pushing each other in each cycle, somewhere here, and rather throughout this whole of this surface, so what is going to happen is on the surface, because of pressing it again and again, surface material may come out in the form of chips, and therefore pitting. Gadda bolte na, pit. So pitting, surface fatigue, that means kind of small chips may come out of that, and therefore surface may get damaged. So what we call this kind of failure, we call it as a surface fatigue failure, or more appropriately you can say that is the endurance limit is going to play a greater role in this case, surface endurance strength, right? So because surface fatigue failure may take place in this situation, so what do we need to do? So normally what we do, how we increase the surface strength of that material, the method that we have is by what we do, we increase the hardness of that particular surface. So we can increase the hardness of the surface. So that is why if you see which of these, it will depend on Brinell is simply a method of like measuring the hardness number. So that hardness, so that means what we can do is surface endurance limit of gear material is dependent on what? That is dependent on the hardness. That is the meaning of this. So not coefficient of elasticity, elastic strength. See, elastic strength could be different of the whole material. What we are doing is we are carrying out the surface hardening. Only the surface portion gets hardened. Why? Because that surface endurance property, we want to resist that. It should not fail in fatigue failure on the surface. Yield strength is not going to affect. Yield strength is the whole strength of that particular gear tooth, right? Okay. So I hope you understood this. Go to this particular. Gear teeth are made harder to avoid what? Try to give the answer and keep it in mind in objective kind of questions, or particularly for PSUs, you have to select the most appropriate one. Most appropriate one. What does that mean? It means that there could be other option which may seems to be correct or may be correct, but you have to select the most correct or the most appropriate one. Okay. See, over here, gear teeth are made harder. Even though we have discussed this, why they are made harder, we want to improve the surface property. So this will cover up not only the kind of abrasion, or that kind of pitting failure. So if you say that whether this abrasion, by making the surface hard, are you improving the abrasion resistance? Of course, it is improving the abrasion resistance. Is it increasing the pitting resistance? Pitting mean what? Surface fatigue failure in the form of pit. Pit means chote gadde, minute pits will be created. That is only after the surface fatigue failure will take place. So if you say, if you make it harder, is it going to improve the? Are you avoiding the pitting failure? Obviously, you are going to avoid the pitting failure. But you know, wear is a more general term which will encompass not only this but this also. So that is why if you will say whether this is the answer, you will say, of course, this is also the answer, this is also the answer, this is also the answer. The most appropriate is going to be the wear, because wear will not only include this, but this, it will include this one also. What? So that is why not A. It cannot be A, because tensile strength. Tensile strength is the material property in the, for example, if I say this is gear tooth. So material is mild steel. Let's say you said that, okay, its yield strength is 250 megapascal, let us say you said. So this whole mild steel material have this much strength. But what I will do, I will surface harden this portion. So do you think that this hardness will get increased? But if you see in totality, it's of this particular gear tooth, this tensile strength will remain same, but only a surface layer which I am hardening, it's this all resistance or will wear resistance, all that will increase, like you're having carburizing, nitriding, something, those surface hardening processes which you can make use of over here. Okay, let's go to the next. Okay, just go to this one. So I think since I have explained it over here, you will be able to answer it. Lewis equation is applied, obviously. To which one it is applied? Only to gear, only to pinion, to stronger of the pinion or gear. So basically, Lewis equation, we are making use of it for the design of the gears, right? So it means we have already seen, sorry, beam strength, that is the tangential tooth load, pi y bm sigma bl owl, right? How we have to decide? We have to decide based on which one is weaker, which one has less capacity to carry this tangential tooth load. Weaker of these two. Okay, same thing. Just go through it. Okay. Now, for this, you need to know, I think somewhere I mentioned about A. Okay, only one of you have answered. Okay, two. A, you are still sticking to pitch line velocity. Module of the gear tooth, modulus of elasticity of gear and pinion. So we'll keep on relating this. Now see, what we said is I am having two ways of finding out the effective tooth load or actual tooth load. How much is that? You said either you are having PT plus PD, calculate it separately, or you are having a method, you said that directly divided by the velocity factor kV. So this we know that how to find out the kV. This one approach we already know, we have already discussed. Other approach is that to find out this value of incremental tooth load, additional tooth load, in addition to this, and add it to this to get the effective or actual tooth load. So how to calculate? We had said that we have an equation called as Buckingham equation. So this is the Buckingham equation where you are having these different factors. For example, C, particularly C, E is the tooth error, B is the width of the tooth, PT is the tangential tooth load. You should know the different terms over here, and V is the pitch line velocity, right? V over here is pitch line velocity, and over here this C term is basically what we call it as the term which is called as the deformation or dynamic factor, right? So over here kV, sometimes we also call it the kV as a dynamic factor, but that is as per Barth, that you have to keep it in mind. Sometimes we call it as velocity factor or dynamic factor. kV also we give this name, dynamic factor or velocity factor. But over here C we call it as a dynamic factor or deformation factor also we call it. Now you can predict. And how to find out the value of C? So this formula that you need to remember over here, where K is constant over here, and this is the moduli of elasticity of pinion and gear, right? Rest terms I think are pretty clear. For example, if you see in this formula, small e is the tooth error in pinion and gear. So let's say simply, let's say it is in micrometer. So let's say I am writing it as a tooth error on pinion plus tooth error on gear. So as simple as that. E. B simply width. So width is going to be same. PT, tangential tooth load, that you have to get it from where? You have to get it from this power equation. That's all. These are the only terms. And V is the pitch line velocity. That's all. Now you can decide very easily. So he has not asked. He has simply had this factor that you can see depends upon what? Depends upon pitch line velocity. No term. This K is constant over here, and this K, that value, depends upon these values. Different. Sometimes see for in these exams particularly. He can directly. Why A wrong? What? Why A wrong? Which one? This one. See, he's asking about C. He's not asking about the PD. Where did he ask about the PD? That PD, that is the dynamic. This dynamic load or additional load depends. Has he anywhere asked additional load depends upon these? No. He has asked about the C. He's asking about the C, and C is over here. So K is constant. So it depends upon moduli of elasticity of this. Had he framed the question, okay, this depends upon this, then definitely I think it would have been pitch line velocity also, moduli of gear tooth also, moduli of gear tooth, and modulus of elasticity of gear and pinion. So all of them are going to be then correct. Okay, and my what I was mentioning over here, remember these values also, because he can frame the questions from here also. Like what is the value of K? K for various tooth forms are, he may say that value of the K in case of deformation factor in Buckingham equation is equal to what? These values he may give for 20-degree full depth, let us say. So you need to remember. So easy to remember, only a gap of 4. 0.107, add 0.004. And over here also add 0.004. So easy to remember. If you remember this, you can simply add the 0.004. For 14.5 is this, and 20 degree full depth and 20 degree stub depth. Factual information that he can ask you. Okay, you should have the background, so you will be able to answer. Now let's go to the next one. Okay, Ritesh, I think we will share the this. I think in group or maybe whatever by whatever means. So I think we will share it. Okay. So load stress factor or material combination factor in gear design is used in. Okay. Now again, this is all these questions are. So you should have the idea where we are making use of this. Okay. Load stress factor or material combination factor in gear design. कहाँ पर use करते हैं? Again, see, in the spur gear design, you normally have two equations. If I say, you are normally basic design when we are talking about, or the, at BTech level, whatever you are studying, you are making use of the two equations only. One is the beam strength equation, that is SB, which is you have already written sigma b y, sorry, allowable into pi y bm, right? This was that. And the other equation is the Weir strength equation. These are the two equations that you are using. All others are like, you are having dynamic factors and all that. They are the modification on this. You apply KV and then you apply this PD and all that. That is to modify this to how to make use of this that is value of increased load in this particular equation. Then the second equation that you are having is the Weir strength equation, which you know dPBKQ, if I remember it correctly. So how to find out the Weir strength of the gear tooth or pinion tooth? So this is the equation. Over here, you know, in this equation, you are having the this diameter of the pinion. That does not mean that it is valid for pinion only. This is valid for both of them, pinion as well as this gear. Okay, and B is the width, K is the this load stress factor or material combination factor, and K is the ratio factor. Okay, the terms you should be clear to you. So he's asking, okay, where do we use load stress factor or material combination factor? That means he's talking about K. In gear design is used in where? Beam strength equation? No, it is not over there. Weir strength equation, we are having this equation both in A and B. Obviously, it cannot be. We are having K term over here only. These are the only two equations that we use in spur gear design. So you can find out, okay, we are going to use it. So answer is going to be same. Okay. Now, keep it in mind, this dP term that I am using over here or in this equation, basically this is not for pinion. This equation is not. What is the Weir strength? Again, Weir strength when we are talking about is the, it says that what is this tangential tooth load that you can apply on the gear tooth so that pitting failure does not take place. Pitting or surface fatigue failure does not take place. That is the meaning of this. Weir strength does not mean something kind of you interpret it in a very different way, but it is simply the, again, what is this? This is nothing but a tangential to what should be this value of load that we should apply so that while they are coming in contact with each other, there should be no surface fatigue failure. There should be no pitting over there. So it is common for both of them because whether it is for gear or pinion, right? When we are talking about in terms of the, so that is why equation is common for both of them. So that is the only difference that you have to take note of, and must understand what is the meaning of Weir strength. Go to this one. Ratio factor in Weir strength equation in the gear design for external gears. Again, in this equation, what was that? Weir strength, you are having dPBKQ. This Q, we call it as a ratio factor, and this value is given by this way. So it will be this 2T divided by T plus T. That means number of teeth on gear, number of teeth on pinion. This is for external meshing, if they are external gears. But if the gears are meshing internally, for example, this is the outer gear and having gear to this way, and you are having one more gear over here inside smaller gear, which is rotating over there, then you're going to use this one to find out the ratio factor for internal meshing. Okay, so over here you're going to have this is the right answer. He may frame the question for K also. Just see this value of K. I don't exactly remember. It is something like endurance strength or something. Properly, I'm not able to recall it right now. But definitely, he can frame the question based upon the value of that. The value of K will be equal to depends upon what. So just see the value of K also. Okay, so let's go to the next one. I think so. Now we are moving on to the shaft design. Okay, these questions are from the shaft design. Okay, which one of the following statement is correct? Go ahead. A. You're saying A? Obviously, you have to apply your this common understanding. When you are having a shaft which is hot, this hot rolled, cold rolled. So, cold rolling or cold working is done to increase the strength of the material, to increase the property, to enhance the properties of the material, particularly like strength, etc. Right? So, obviously, that you can understand. So, if we are making the shaft based upon that, then obviously it is going to have that particular through cold rolling. Then obviously we can say its strength will be more than hot rolled. It is the same case for your like sheets also. For example, if I am having a hot rolled sheet or hot rolled coil, and I'm having a cold rolled coil with me of let us say steel or aluminum, whatever, then if I ask you which one is going to have in general, right? So which one is going to have the higher strength? Then you will so obviously in general, if you say, then cold rolled coil is going to have the higher strength because I have plastically deformed that material, right? The same is the situation for shaft also. So it is straightforward. Okay. So which one of the following statement is correct, right? Okay, give me the answer for this. Just go through it and apply your. There are going to be many questions where you have to apply your common understanding, and if you will think a little bit, I think you will be able to reach the conclusion. A shaft is subjected to what kind of stresses a shaft is subjected to? Give me the answer. Okay, so I think all of you are on the right path. That means it can be subjected to any of these stresses. It will depend upon the type of loading. He has not given you the loading. What kind of loading I am applying? If I am applying pure bending, then only bending. If I am applying pure torsion, then shear. If I am applying bending as well as the torsion, which is in most of the case you are going to have this situation, then obviously all of them. So depending upon what kind of load I am applying, shaft can be subjected to any of these particular stresses. So it means D is going to be the correct option. Just try to answer this. Just apply your this concept and try to solve this. Two shafts A and B are made up of the same material. The diameter of the shaft A is twice at that of diameter of shaft B. That's what it says. Twice that of the power transmitted by the shaft A will be. Let's say this is how it is. So, but he has mentioned the diameter of the shaft is, sorry, he has given is they are made up of the same material, right? When they are made up of the same material, then obviously you can say that the allowable value of the stress is going to be same, isn't it? Allowable value of the stress is going to be same. Let's say, for example, let's say if it is subjected to torsion, then torque transmitted capacity is given by how, you're having 16 okay, shear stress, I think we give this way. I think shear stress is equal to 16 mt divided by pi d cube. Am I correct? This is how we do, right? So how I can find out the this torque, because I have to find out the power. So if I can somehow I can find out this value, then I can say torque is going to be, I can find out torque from here. It depends upon what? So it depends upon directly proportional to d. I can say torque pi d cube divided by 16. So directly proportional to d cube, right? So that means torque is directly proportional to diameter. If this information you can figure out, then obviously, then if torque value increases, then obviously power will increase. If torque value will decrease, then power value will decrease. So just you can compare it for these two shafts accordingly, right? The same thing I have displayed this over here. Just have a look. Okay. Right? So power, so it means torque is equal to, I can write it this way. So obviously torque depends upon diameter. Now when I talk about the shaft B, then torque is in terms of directly proportional to dB cube, whereas for the shaft A, he's saying the diameter of the shaft is twice as that of the B. So I'm writing it over here. That means it is going to be 8 times. So when I will input over here, then torque over here, torque transmitting capacity is going to be 8 times the torque. So torque transmitting capacity of A will be 8 times the torque transmitting capacity of B. So if torque transmitting capacity is 8 times that of B, then obviously power will also be twice 8 times that of B. What? So it means this is going to be the correct answer. And keep it in mind, since why I am comparing, this is constant. Keep it in mind, when I am writing the stress, this will become the stress mean allowable maximum value of the shear stress that shaft can carry. This means this becomes constant. This is constant. This is constant. So only variable over here is D. Since two shafts, both the shafts are having the same material. So it means this is constant. So I can directly interpret directly based upon the diameter for the torque, right? That is why I wrote directly proportional to d cube, because all these other factors are constant, because this is going to be constant because both the shaft has same material. Therefore allowable value of the shear stress for the both the shafts is same. What? Okay. So okay, just go through this. According to maximum shear stress theory, the maximum shear stress in the shaft, maximum shear stress. So, if you have studied that how we give up, if you see the terms over here, he's talking about here you are having the normal stress as well as torque. It means shaft is definitely getting subjected to a combination of normal stress and shear stress. So normal stress, it may be bending or it may be axial, that we don't know. In any case, but we know that okay, definitely it is going to be a combination of either bending or shear, or maybe axial or shear, whatever. So that is why if you see all of them are having these terms sigma and tau. So when you are having a complex loading case, how you give the value of this normal stress? How you give? You give value of the this principal stress. You have already studied in SOM also. Like for example, had it been the sigma, two values of like sigma and sigma y also. Let's say sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 square plus tau square, right? I think this was the right. This is how this is. Now, so in this case, since you are having only normal stress is only one, that is either it could be bending or something. So I can ignore any one of them. So I'm left out with what? I'm left out with, let's say if I ignore y, I am having only one normal stress. So I can say sigma by 2 plus sigma by 2 square plus tau square. This is how the situation is. So this is for the normal stress, that is the principal stress. And also on the similar line, you know, if I have to write the maximum value of the shear stress in this case, in complex loading case, then maximum value of the shear stress is the this term only. So this term means sigma by 2 square plus tau square, this term. So if you take out half outside, I think it is going to be sigma square plus what? 4 tau square, right? So 4, if it is going to be this, okay. So when it will go 4 will cancel and this, so, right? I'm correct. Another point. So as per the maximum shear stress theory, the maximum shear stress induced in the shaft will be this much. Normally this is this portion of this. So if you know this equation for principal stress, then maximum value of the shear stress as per the maximum shear stress theory will be this particular or this later half of this, right? So this is used in case of the complex loading cases where you are having a combination of sigma and tau. Okay, so I think I have written the same thing over here. Only thing is sigma 1 is this one, so you can write anyway this way. Now on the similar lines, the question could be framed this way also. Just see, when the shaft is subjected to combined twisting moment and bending moment, then equivalent bending moment is equal to what? So see, you know this again, the same thing, only difference is going to be, just have a look over here. I think you may have, if you have remembered the formula, you are having this value of principal stress and this is the maximum value of the shear stress. From where we got this? You know, bending stress, shear stress I can write this way, 16 MT by pi d cube, that I had written when I was explaining you, and same way like bending stress I can write it 32 MB by pi d cube. From where I got it? Because you know sigma by y is equal to m by I. For shaft I will input the value of this and this, so I am going to get this one. Same way tau by r is equal to T by J. I will pull moment of inertia and value of r. So this is going to be the maximum value of the shear stress, and this is going to maximum value of the bending stress. So either I write in terms of stress and write this formula, or I can directly, if I know the torque value or if I know the bending value, the bending moment value, I can directly calculate these values, right? So if you know this, that how I can write the bending stress in terms of bending moment, how I can write the shear stress in terms of torsional moment, then just input this value on the sigma 1. How was the sigma 1? You wrote sigma by 2 plus sigma by 2 square plus tau square. This is how we wrote. So what you do is simply input the value of sigma bending over here and tau over here. Then in terms of bending moment and the torsional moment, this is going to be this one. Same way, this tau I can calculate. This is the second part of this one, that is sigma by 2 square plus tau square. So if I input this value of sigma b over here and this over here, so tau I'm going to get, this is the maximum value of the shear stress. So keep it in mind, this is the maximum value of the shear stress when this is also the maximum. Keep it in mind, this tau is in itself maximum, but this is what that you have externally applied to the shaft. And you know where it is going to have, because in the shaft everywhere you are not going to have the same value of the maximum shear stress. You will say it is going to be at the periphery. So that is why you have to take the diameter. This dia is coming in the equation, right? When you will input it in the tau by T by J and tau by R, right? So this also is the maximum value of the shear stress on the shaft or at any point on the periphery. But if I take any element on that periphery in which you are applying this maximum value of shear stress and this maximum value of the bending moment, then what is the, you know, let's say this is the shear maximum value of the shear stress and this is the maximum value of the bending moment that is acting, then there is going to be some plane inside this material where you're going to have the maximum value of the shear stress. And that maximum value of the shear stress in that element that I have taken on the surface is this one. So you should have clarity what is the meaning of this tau and this tau. So that is, this clarity you can get it from the this strength of material where you are having that topic complex stresses. There is very clearly you will realize that. But anyway, now if I will input these values over here, then I'm going to get this one. Now, so that means it is easy for us because if I know the bending moment and torsion moment, directly input the formula instead of separately calculating then inputting, it will become easy for me. Now, when you are having, now I hope you have got it. Now, my point was over here, just have a look. So, over here, this portion in the principal stress, maximum principal stress, we call this as a equivalent bending moment. This term, we call it as a equivalent bending moment. And this portion in the maximum shear stress, we call it as a equivalent torsional moment. Okay, so it means when a shaft is subjected to combined twisting and bending moment, M, the equivalent bending moment, so equivalent bending moment term is going to be this one. Had he framed the question, what is going to be the equivalent torsional moment, then your answer should have been this one. So now you can just check it from over here. I think this is going to be that answer. B. Shubham, I think now it is, this is C, not C, this is D. Just C. Why it is C? Why is it C? Why you are saying that this should be C? You have this equation over here. You have clearly this equation with you. So now pretty clearly you can say this term, we have given this name, this portion name as the equivalent bending moment and equivalent torsional moment. Sir, it should be 32 in the expression for bending stress. Just cross check it. So it is 32 over here, but when you will input that over there, I think that is divided by 2. Again, it is divided by 2. See, over there, sigma b by 2 plus sigma b by 2 square plus tau square, right? This is sigma 1, right? Sigma b is going to be 32. 32, again, this becomes 16 mb by pi d cube plus, just see, because you are having 2 down there, so it becomes 16 mb by pi d cube square plus 16 mt by pi d cube square. So where is the trouble? So when you will take out 16 pi d cube, 16 pi d cube square, it will come out common 16 divided by pi d cube, so mb into this. So there is no I think this formula is not wrong. This is exactly same. You just take it out. What you are going to take it? Because you are having 32. I am inputting the value of 32, but down there is 2 also. It will cancel. So it becomes 16. So 16 this. Inside also same situation because it is 2 over there. Over there is only no 2, but you are having only 16. So if you input it over here, you are going to have this one. Okay. So just cross check it, but I think this is going to be the correct, whatever I have written. But for safety side, if you want to cross check, you can cross check. But I hope this is correct, whatever I have explained you. Okay. No. Badil, it is not going to be, it is going to be 16. Why it should be 32? I have already input the value and then shown you. Just cross check it. You just solve it, you will get it. Okay, let's go to the next one. Okay, just have a look. The bending moment M and the torque T is applied on a solid circular shaft. If the maximum bending stress equals to maximum shear stress developed, then M is equal to what? Okay, so I think you can straightforward get it, because you know bending moment if the maximum shear stress, so maximum shear stress becomes equal to bolta hai, if it becomes equal to maximum bending stress, then how much torque and this moment bending moment relation is going to be You know, in case of a torque, it is going to be mt divided by pi d cube, which is equal to what? You are having bending stress 32 mb divided by pi d cube. Cancels 2. So it means what is asking me to calculate? M. So mb is going to be mt by 2. A. Gotham, just check. I ask you to cross check. If you find it wrong, just cross check. Okay. Okay. Can we go ahead now? Okay. The same thing over here. Okay. So let's have the next question. Okay. Go through this. Maximum shear stress developed in a solid circular shaft subjected to pure shear is 24 megapascal, 240, sorry. If the diameter of the shaft is doubled, then the maximum shear stress developed due to the same torque is how much? Maximum shear stress developed in the solid circular shaft is this. So maximum shear stress, it says developed is, let's say 240 megapascal. And how do you write it? Maximum shear stress? Maximum shear stress, you write it in terms of what? 16 mt divided by pi d cube. This is how you calculate. And what it says, if the diameter of the shaft is doubled, right? So let's say if I say this one, maximum shear stress developed is, its d1 was the initial diameter. Now if it is doubled, then what is going to have? So the maximum shear stress developed, then the maximum shear stress developed due to the same torque. So it means if this was this, maximum shear stress developed will be equal to what? 16 mt divided by pi. Now diameter is doubling, pi times d cube for the same torque. So it means if you see over here, I am having 16 mt divided by what? You can have 8 times 8 pi d 1 cube. Now this term, this one, 16 mt pi d cube, 16 mt pi d 1 cube is 240. So that means 240 divided by 8, 30 megapascal. Am I clear? See, okay, good. So I think it is simply the common understanding that you can make use of. Okay, so just go through this question. Go through this particular question. Okay, a circular shaft is subject to a torque T and the bending moment. This, the ratio of maximum, I think this is straightforward. You must be able to answer this. Almost straightforward. The ratio of maximum shear stress to the maximum bending moment. Again, the same thing. Maximum shear stress to, what he says, maximum shear stress to maximum bending moment. So you know it, maximum shear stress 16 mt by pi d cube multiplied by 32 mb pi d cube. So it becomes, he is saying this torque. Okay, good. So torque, he is representing this. So T divided by 2 mb, he is representing it as m. T by 2m. See, it should be B. Check it out. It should be B. So simply the ratio B. Okay. Just see. Simply you have to take the ratio, that's all. Divide by the ratio of maximum shear stress, tau divided by sigma B. Okay, good. Transmission shaft includes what? What does it include? Just see. Give me the answer. Go on just doing in parallel. You need to answer. So transmission shaft includes. See, the meaning of transmission shaft is what? You are transmitting the power, as simple as that. The names are different. You are naming them differently. That is the only difference. For example, just have a look. What is the meaning of counter shaft? What is the meaning of line shaft? Line shaft means you are having a shaft, long shaft, for example, over here, and you are having midpoints from where you are taking out the power. So it could be like you are having different pulleys, and by making them use of them, you are running different devices. So if I ask, you are having a common shaft, and from that common shaft, which is being run by a motor, let us say your power source, from that common shaft at different points you are taking out the power. So I can call that shaft as a line shaft. Counter shaft, for example, if you are having a gearbox over here, this is the shaft which is coming from the engine shaft, or a crankshaft that you call it. And from there, when you have to transmit the power to the output shaft in the gearbox, you are using to engage the gears, right? You make use of another shaft parallel to this one. We call this shaft as a counter shaft. And you are having an overhead shaft. Overhead shaft is nothing but a kind of line shaft only. Only difference being it has been installed at a overhead location. That is the only difference. So all of these shafts are basically transmission shafts only. So transmission is a general term. That means you are making use of the shaft to transmit the power. But these are different forms of these transmission shaft. Got? Okay. So let's go to the next one. Give me the answer. So now we are moving on to the bearings. So give me the answer. Deep groove ball bearings are used for. Out of these, which one is going to be the proper combination? When we talk about the deep groove ball bearings, that means deep groove ball bearings. So obviously, this is the configuration. All of you have seen these bearings. So this is a deep groove ball bearing, right? So since you are using the balls, so definitely, point contact is there between these races. All these different elements. For example, this is the outer race, this is the inner race. This is you are having this cage, or what we call as a retainer. And these are the balls which are using over here, having the point contact. So since friction is less, I can run it at a higher speed relatively, right? So these deep groove ball bearings can carry both thrust as well as radial load, but moderate. Both of these loads can be carried at a of moderate capacity. That means, for example, if this load is radial, obviously you can just simply understand because it is passing through the axis, so it can carry. But if I apply some load over here, only difference is going to be this ball can little shift to one direction, but still it can carry load. It means if I am having this moderate load and this is also moderate, this load cannot, if it is very high, then this, because of point contact, it can damage. So that is why you are having, if you want to have a high radial load carrying capacity, then what do? You go for the line contact where you are having the roller bearings. So it means I can say that for moderate thrust and moderate radial loads, I can go ahead with this particular ball bearing or deep groove ball bearings. So if you see heavy thrust load, in any case I cannot take, because if the thrust load is heavy, then this will shift this ball towards this edge over here where you are having this this race edge, you can say. So it will try to create the noise and therefore it is going to damage it. So we cannot have small angular displacements of the shaft. No, it cannot. If you have to have a, it cannot. This means angular misalignment means this one, this shifting of shaft. No, it cannot accommodate radial loads at high speeds. Okay, it can carry radial load at high speed. That is okay. If I say whether this statement is correct or not, statement is correct. But the most appropriate is going to carry this one because it can carry both the loads. So this is also correct. But the most you can say appropriate is going to be because it can also carry the moderate thrust load at high speed. Okay. So let's so yes, C. Why you are saying C? Okay, C is also the correct answer, but as I told you that you have to find out the best answer out of all those options that you are having. Go to this particular question. Where the following bearings are preferred for oscillating conditions? Now, I don't know whether you are having a idea of oscillating condition or not, but here is the bearing. Anyway, you can see the answer also. So okay. So if you, I don't know whether you can guess it or not. This is the engine where you are having these valves which will be down there, right? And this is a this counter shaft over here on which we have this rocker arms, right? So over here, these rockers arm will push this. This is a spring over here. This push this downward and it will open the valve. That is the inlet and exhaust valve that you are having in the engine. So it can move this way. So you are having a kind of hinge over here where it can move this way. Okay. So this kind of motion. So in each of these particular valves, while valves opening, you're having this rockers arm over here, where and down there, you're having a camshaft. These are that means exactly down there, right? So this motion is basically what we call it as a oscillating motion. So for these kind of situation, we are having these, and also over here, we are having particularly specifically, this is one of the application of needle roller bearings, because straight, these are the roller bearings, cylindrical roller bearings, their diameter is relatively large compared to this one. Here diameter is small, right? So when the space is limited, so we cannot have that much ball having a higher diameter. So normally what we do is we employ a rollers of smaller diameter. So they are having significant radial load carrying capacity because line contact is over there. At the same time, what we can have, we can save the space over here, and over here you are applying that one over here. Basically, this is the location where at that particular point where it is this oscillating this way. So here we are having the bearing. Same way over here we are having this bearing, this one. Same way over here we are going to have this bearing. So we are having a rollers, needle rollers. Name is given as needle rollers. Why? Because their diameter is very small, like needles. So space saving also takes place. At the same time, when these rollers, because we don't provide the cages over there, so when in one rotation they go forward, and when it reverse, then they will come to again their own position. So that way, that means kind of they don't gather at one location or in this particular kind of motion, and therefore friction cannot be that much over there, right? So these kind of needle roller bearings are used where you want to carry a significant radial load, as well as where you want to have a very limited space, for example over here. One more application is going to have that I will discuss with you in the coming questions, but over here I think that is more than sufficient. So it means the correct option is going to be the C. So oscillating motion, you are going to have this kind of bearings that you are going to use. Go to this particular question now. See what it says. You are having to increase the capacity of a ball bearing. Dash is provided to increase the number of balls in the bearing. So what mechanism do you provide in the bearings, particularly in the ball bearings, so as to increase their load carrying capacity? Capacity means what? Obviously load carrying capacity. Any answer? Okay, in case of ball bearings, particularly, you're having this situation. How you fill those balls inside the two races. For example, this is outer race and inner race. So this is the situation. This is how we fill up that. So we shift the inner ring to one side and then fill up with those balls. But by this mechanism, we can fill this space and then we will adjust it. Then we'll bring this downward, this inner ring downward and adjust it, and then we'll provide that particular cage and all that. It means by this method, a limited number of balls can be introduced between this ring and this ring. This is the method of filling those these balls inside these particular two rings of the ball bearing. But let us say if the load that it has to carry is more significantly high, then we have a mechanism that if we increase the number of balls inside it, then I think that problem can be handled. So for that, what we do is we cannot approach that way, because only, let's say over here 1 2 3 4 5 6 7 8 9. Let's say if I want to increase the load carrying capacity, so I want to introduce 12 balls. I cannot introduce by this method. So what we do is, in the inner race and outer race, we provide a notch over here. We are cutting it, and then we are introducing the ball. So I think any number of balls I can introduce this way. So I'm introducing the balls from here. That's all. So once I have introduced, now I have the retainer. This is the retainer, right, which is catching them. Over here you can see. So balls are inside this retainer. So I am then applying the retainer. So they will not come out of this notch also when it is in the running condition. So the mechanism to increase the load carrying capacity of the ball bearing is to increase the number of balls inside that particular two races. And the method that we can adopt is called as notch, introduction of the notch, that is the filling notch we call it. So notch means this particular slot that we have created, and we fill those balls through that particular this portion, right? So C is going to be the correct answer. Okay, right? I hope you understood it. And they will not come out. If you have doubt that, okay, since you have created a notch over here, when they will run, it will not come out. How it is going to come out? Because the retainers that you have used, that is catching a hold of those balls, they will not come out even the running condition. That you can see over here also. See, just see this one. Which one of these following is not a correct statement? Correct statement कौन सी नहीं है इसमें? Not a correct statement. Just go through it. So I think most of you are correct, right? The balls in the ball bearing remains in position due to centrifugal force. Where is the role of centrifugal force in retaining? The role of retaining the balls. Who is retaining the balls? Who is retaining the balls? Who is retaining the balls? This is a retainer. This cage, this which is holding it. So retainer or cage is retaining the balls, not the centrifugal force. Even if it is rotating, so they are going away. So it has nothing to do with the retention. Retention is done by this particular cage we have provided so that they don't go away, right? So it means this is not the correct statement. Which of the following is not the correct statement? The balls in the ball bearing remains in the position due to centrifugal force. This is incorrect. Cage is made the hardest of all the parts in the ball bearings. Why it is made the hardest part? Because this cage is holding those balls, and balls will be rotating in random motion while it is rotating. The whole assembly will be rotating except the one of the rings. For example, if this is fixed, then inner ring will be rotating, and all these balls will be rotating along with the cage, right? So when all them rotating and the balls will be rotating in a random motion, then obviously since it is retaining, so it is going to rub against this particular retainer also. So it should be hardest. It should not create the erosion of the surface. That is why it should be made of the, it is made up of the hardest material. Spherical roller bearings have the capacity for self alignment. Okay, I will show you over here. Just see. Spherical roller bearings have capacity for self alignment. So I hope you know, in case of spherical roller bearings, what we do is the outer cage is made this way. For example, it is having double spherical roller bearing. This is double spherical roller bearing. You could have single also, but the outer race is made this way, right? When outer race is made this way, now what is going to happen is, you know, when you are having a shaft which is over here, which will swivel this way. So these rollers or these spherical rollers can easily glide over this surface, because this is the inner race which is fixed to the shaft, and these are the rollers. You can say these are the spherical rollers. If you want to see over here, the whole of the assembly, if it goes this way, the shaft goes this way, then they can easily, if you see over here, it can easily swivel this way. So it means spherical roller bearings have capacity to for the self alignment. That means they can align as shaft. See over here this way. If shaft goes this way, they can align easily. That is the meaning of this. Okay, so this statement is also correct. Roller bearings have higher load capacity than that of the ball bearings for a given overall size. That you can get the idea, because why? Roller bearings have higher load capacity. Why? Because there is a line contact. Whether it is a spherical roller, whether it is a cylindrical roller, compared to ball bearings. Always, because ball bearings are going to have the point contact. So when load will act, it is acting at a point. So think of a situation, if the whole of the load is acting at this point on my this hand, so I'm going to feel the pinch over here. But if the same thing is this way, you apply the load, it will get distributed along the line. So which one is going to have more load carrying capacity? You will say roller bearings are going to have the higher load carrying capacity. So these statements are correct. Go ahead. The life of a ball bearing at a load of 10 kilonewtons is 8,000 hours. Okay, so I think you have to make use of, this is the load life relationship that you are having in case of these rolling element bearings, right? That you know. And how do we write that equation? You know, rating life of a group of identical bearings is given by C divided by P, equivalent load raised power P, into either you write it as million revolution, और either you write million means 10 लाख. 1 मिलियन कितना हुआ? 10 लाख. आप बोलते हो ना कि 1 मिलियन व्यूज हो गए, मतलब 10 लाख व्यूज हो गए. 2 मिलियन व्यूज 20 लाख. So that means how much? 10 is power 6. So this is basically 10 is power 6 is million. That means 10 lakhs, right? Revolutions. So that means this is the rating life of a group of bearing is given by this, where you should know the terms. This P is, I think, 3 for ball bearings, and this is for 10 by 3 for roller bearings. This is how you should know ball bearings, and this is for roller bearings, that you know. And over here, C is the dynamic load carrying capacity, and P is the load, actual load which you are applying on the bearing, right? So actual load that you are applying on the bearing, this is a dynamic load carrying capacity of the bearing. Now he's saying if the life of ball bearing at a load of 10 kilonewton is this. So 10 kilonewton is what? The load that you are applying, this one. If the life in us, if the load is increased to 1, now if this is changed, so I can write it this way also. So let's say instead of writing in a standard format, I can write it this way. Let's say L1. Why? Because I am having different loads, so I am writing this way, C divided by P1. Let's say instead of writing 10 is power 6, I am writing it as a, it's up to you, right? Because this is a ball bearing, so I can say this is 3. Ball bearing, so it is going to be 3. 10 is power 6 if you want to write revolution. Let us say what is going to be the life of the bearing if the load is increased to twice. So C is the dynamic load carrying capacity, right? So this dynamic load carrying capacity is same for identical group of bearing or for the same bearing, it is not going to change. This data is compiled in the that manufacturer's catalog, and for each bearing or for a identical group of bearings, either the group of bearings which are identical or it is the same bearing. So for that, the dynamic load carrying capacity remains same. It does not change, right? And this is the actual load that you are applying. So it is saying that I'm applying the load P2. Rest is same. So what it says, I want to find out if the load is increased to this, keeping all other conditions is same. So what is asking me to, if the load is, what is asking me to calculate, its life in hours. That means I have to find out L2. So I can write it this way. If you write it L2 by L1, how I can write? So they are going to be cancelled out. So L2 by L1, that means it is going to be P1 by P2. L2 P1 by P2. It is going to be P1 by P2. Raised power 3. Am I correct? This will cancel out. So P1 is how much? P1 is how much? P1. Initially 10 kilonewton. P2 is how much? Load is increased to 20. 10 is power 3. 1 by 8. Am I correct? So that means he's asking me to calculate L2 in hours. So L1 in hours is given. So L2 will be equal to what? L1 is how much? 8,000 hours. So 8,000 hours divided by 8. So how much is that? 1,000 hours. Am I clear? So C is going to the correct answer. Okay, so simple relation that you have to make use of over here. Okay, same way I have solved it over here also. The only thing that you have to keep in mind, if the bearing is same and if I'm subjecting that bearing to different loads, then P is going to be this, because this is the actual load that I'm applying, that is going to change. But since bearing is same, so dynamic load carrying capacity is going to remain same. So Shubham, I think either it is over there, I don't know, I need to check, either it is already there in the panel which is given to over there. I don't know whether it is, that has been already uploaded over there, given to you or not. But even if it is not given, then whatever we have covered, I think that whole in compiled format we may upload in the panel and you can access it, or you may download it. So I need to check how you can access that. Okay. Okay. Shall I go ahead? Okay, done. Now go ahead with this question if that is clear. Is this question different from the previous one? Is this question different from the previous one? I think no, isn't it? This is not different. Only difference being, in earlier question it was the same bearing subjected to different loads. In this case, it is the identical bearings, group of identical bearings subjected to different loads. So if it is a group of identical bearings, that means their dynamic load carrying capacity will be same. The same thing. So can I say over here, it is going to have the same thing like L1 will is equal to, I had written, so I am writing directly. So L1 by L2 was how much? P2 by P1 raised power what? I think it is ball bearing, 2 ball bearings, so I am taking it 3. So rest is, so how it is going to be the ratio? He is saying that the ratio of the life of the bearing P, 2 identical P. So I am writing it P by Q. That I have to find out. So P Q divided by PP raised power 3. So ratio of LP by life of bearing Q. Q कितना है? Q is 45 by 33. So 3. Right? B. Clear? Same thing. Again, same thing. Only difference being over here, I'm writing in terms of P and Q. C will cancel out because dynamic load carrying capacity is going to remain same. None? Okay. Okay, so we can go ahead now. Okay, same thing. Either you write it in million revolutions or either you write 10 to the power 6 revolution, meaning is same. Just see this. Read this statement carefully. Read this statement carefully. It says that when shaft rotates in anti-clockwise direction at slow speed, in a bearing, it will what it is going to have? In clockwise direction, anti-clockwise direction. Anti. So this is the initial position, you know, all of you know. The shaft will be resting on this. Here you are having the fluid. So, you know, initially there is going to be metal to metal contact. This is a case of hydrodynamic general bearing. So, initially there is going to be metal to metal contact. There is no lubricant between these two surfaces. So, when it will start rotating, this way. So, over here, it will climb this surface because of friction. Because you will try to rotate it this way, because of the friction over here, it will try to climb in opposite direction. So, normally when initial that means when the speed is low, that time initially when you start rotating it, it will climb in opposite direction because of friction resistance that is offered by the surface, this surface. So it will slightly shift in this direction, but when the speed will go on increasing, then pressure due to the rotation of this will go on increasing, and then finally when over here pressure becomes significant, then it will push it to the other direction. So the final running condition is going to be this way. Just see, have a look. So this is the rest position at the bottom. Keep it in mind. Let's say this is resting bottom. So initially when the speed is low, it is going to move in a direction opposite to its rotation, because of friction resistance over here, it will move, it will try to ride over the other surface. So it will move in this direction. But when sufficient pressure will be built up over here, then that pressure will shift it to the other direction. So in running condition, full running condition, as you know, the eccentricity is going to be on the other direction, this side. So over here, he's saying the shaft is rotating anti-clockwise direction, this at slow speed. In the bearing, it will have a contact at the bottom most of the bearing. Obviously, not at the bottom most, because it will move on one direction. So D is the option, that is that move towards the left. So obviously anti-clockwise rotation, so it will move towards the left initially because of friction. But had it been this question been the running condition, then your answer should have been, you have to see the rotation, okay? Pressure will develop over here, so full running condition, it will move to other direction. So then it will move to the right. But over here, it will move to the left. So this is going to be the correct answer. Same is going to be the situation if we change the direction of rotation. Okay, had it been this way, just look at this now, okay? I'm not talking about this rotation. So I'm saying this is not the rotation, okay? I'm saying this is how the rotation is. Clockwise. If the rotation is clockwise, then obviously initially this surface will offer the resistance. So it will move on the surface. That means initially it will move to right. It will try to climb this. But when the full running condition, when the significant pressure will be developed over here, significant pressure will increase, then it will be moved towards the left. So in running condition, then it would have moved in this direction if the rotation is clockwise. So these 4 questions could be framed to you. Okay. One is for anti-clockwise rotation in running condition and rest condition, not running condition and slow initial speed, and the other one is the clockwise rotation, slow initial speed and then running condition. Go through this. In an oil lubricated journal bearing, the coefficient of friction between the journal and the bearing. So you should know this variation of coefficient of friction, and I think you may be knowing. Yes, wedging action, obviously because of the pressure will be developed due to the wedging action. So wedging action to be on the direction in which you are rotating, in that direction, in that side. For example, if you're rotating clockwise, anti-clockwise, so in this direction you're going to have that pressure development because of wedging. So okay, so this is the graph. I think this was drawn by the Mackey brothers, you know. So here you should have a very clear idea of this. That is coefficient of friction versus this bearing characteristic. Okay, so this is the mu n by p. This is a bearing characteristic. This is a dimensionless number. You know, when you plotted that graph, then initially, you know, you're having a high friction. So as the speed increases, then you are going to have a, basically this is for the different combination of coefficient or this viscosity over here. Just keep it in mind. Mu is not the coefficient of friction, it is the viscosity, dynamic viscosity. Coefficient of friction is F. So that is the difference over here. N and pressure, you know. So you are having, as you increase this total value, then there is going to be a region where again the coefficient of friction will increase. So we say that this is a transition zone over here, and in this side this is a what, thick film lubrication region, and this is a thin film lubrication, or we also call it as a boundary lubrication, because metal to metal contact will be over there, so friction will be high. Whereas over here we call it a thick film lubrication, because there is going to be both the surfaces are going to be separated by a thin layer of lubricant. So that is why we say that it's a thick film lubrication, or we also call it as a hydrodynamic lubrication, or we also call it as a stable lubrication. Why? Because when you are operating in this region, then if there is any change in this all of these particular parameters, it will not shift easily into this particular zone where you are going to have the very high friction. So this understanding you are going to have. And the other part is that the point where you're going to have the minimum value of coefficient of friction is this one, right? So see, this is the minimum value of coefficient of friction anywhere on this. So corresponding to that minimum value of the coefficient of friction, the value of mu n by p, we call that as a bearing modulus. So that also you should have the idea. You can frame the question from there also. That is what is bearing modulus. That is the minimum value of the coefficient of friction. Not coefficient, minimum value of the the value of the mu n by p corresponding to the minimum value of the coefficient of friction, right? So in this case, coefficient of friction between the journal and bearing becomes minimum at the optimum speed, and then increases further with increase in speed. So let's say even if we keep the other parameters constant, we see the variation if we will increase the n. As we go on increasing the n, then there's going to be a point where you are going to have the lesser value of friction, least value of coefficient of friction. So, and then after that it go on increasing. So D is going to be the correct option, right? Okay, let's go to the next one. Just see this and try to answer. Journal bearing of diameter 30 mm, supported in sliding bearing, has a maximum load. So these values are given to you. So he's asking you to calculate the length of the sliding bearing. So basically he's talking about the sliding contact bearing or a hydrodynamic journal bearing. So you already know we are having this one, right? So this is a shaft, let us say, inside that. And let's say the load is acting W. So how do you write the pressure? If I want to ask you, how do you write the pressure inside the bearing? And this value is the average pressure, you know. Average pressure inside the bearing, you write in terms of load divided by area. Load divided by area. But which area? In this case, we take the projected area of the shaft, right? And the projected area of the shaft is what? For example, this is the journal that you are having, shaft that you are having, and this is the bearing, and this is the length of the bearing, right? Same thing. This is a side view. This is the front view, let us say. So this is the length of the bearing, and this is the you are having. So diameter is this one, right? So when we say that, okay, what is the area which is getting, the pressure is getting generated, then you will say when you are applying the load on this, when you are applying load on this particular shaft, so over there you're going to create the pressure, and so load divided by area. Which area? So lower half, when you look at it from the top, it will look like a rectangle, right? A rectangle of what? For example, if I look on this pen from the top, same situation over here. So I will find that, okay, I will find the rectangle over there, and the rectangle will be of this width, that is diameter, and obviously length is going to be the length. So that area we call as a projected area. Like projecting means, like if you throw the light from here, then over there you will see the rectangle. So that is the projected area of this particular pen, which is of circular section. So it means this is the D into L. That's all. So he has given you that, okay, find out if pressure is given inside the average pressure inside the bearing. So W is the load that you are applying, and then you can find out the length of the bearing from here. Am I clear? So just have a look over here. Just you need to input the values relevant. Just keep the unit same. That means same means either in mm or whatever we want to keep it. Clear? So I think E is going to be the option. So just find out the value of L. Done? Okay. So let's move ahead. So only thing I think over here that you need to remember, in case of journal bearings, when we calculate the pressure, which area you need to take. So you should keep it that we take the projected area. Okay, go ahead. Anti-friction bearings are, which one of these are the correct? Which one of these are the anti-friction bearings? Okay, so see, the name anti-friction bearings are given to the rolling element bearings. Why anti-friction? Anti-friction does not mean that they don't have friction. The only meaning they are having is that they are having very less friction. That is why they have been given the name called as anti-friction bearings. That is a rolling element bearings. So out of these, which one is the rolling element bearing? So rolling element is the ball and the roller. So either they could be ball bearing or they could be the roller bearing. So C is going to be the correct answer. So, and one more thing that you should remember, that you should not interpret this anti-friction as there is no friction. No. The meaning of anti-friction is there is friction, but friction is very less. Okay, give me the answer, even though I have explained you somewhere, but just give me the answer. So ball bearings are provided with cage. Cage means retainer. What is the purpose of providing the cage? To reduce friction, to facilitate slipping of balls, to prevent the lubricant from flowing out, to maintain the balls at a fixed distance apart. See, the purpose of providing this particular cage is that those balls should not come together, right? If you see over here, in this case, the cage that you are having over here, so it will keep them in a fixed position. For example, even though, you know, this cage will be, these balls will be moving, this whole system will be rotating. So, but these balls will not come out easily because these retainers are holding those particular balls in the position, at fixed positions. So even while rotating, these balls are going to remain they're going to maintain the fixed location, and they will not going to come together. Because if you will not provide the retainers, the balls may come together and they will try to rub against each other. So when they will rub against each other, then the value of the friction will increase, and there are going to be a lot of friction loss. Just see, anti-friction bearings. Okay, which one of these statements is going to be correct? Have low starting and low running friction at moderate speeds, have high initial cost, can carry both radial and thrust loads, all of these. Okay, see, when we talk about the anti-friction bearings, you know, let's check these statements one by one. They have low starting and low running friction. Why? They're going to have low because reason being either point contact or line contact, and in this case you're going to have the friction, less friction. At moderate speed, see, moderate for this is applicable for moderate speed. If speed is very high, in that case centrifugal force will act and therefore normal load will increase. For example, if you are having this over here, so if these are the balls, so you know friction will depend upon what? The load which is acting at the point of contact and the coefficient of friction over there. So if you are having a very high speed, then obviously centrifugal force will acting will be more. So normal load will be more, even though that is the static friction coefficient is same. So total value of the friction over here will be more. That is why if the, so this is correct statement when you're having a moderate speed, not at very high speeds. If the speeds are very high, then you're going to friction may increase. Have why high initial cost? Obviously, because why? Because you are making all those elements separately. Because this is being, he's comparing this with respect to what? With respect to the sliding contact bearing and all that. So in sliding contact bearing, you are having a simple bush. That's all. And you are having a shaft which will be running inside that. That's all. So it means in this case, the cost of the bearing, anti-friction bearings, you have to prepare different elements separately, case, then balls, retainer, etc. separately. So cost is more. Initial cost is more. Can carry both radial and thrust loads. Okay, we have discussed they can carry both the. It means all of these options are correct. Now I think similar kind of questions we did somewhere else also. Okay, similar kind of questions we did somewhere else also, but I think piston pin bearings in a heavy duty diesel engines are. For that you need to have the idea of piston pin bearings. Basically, where is the location of the piston pin? So you know this is the connecting rod, right? So this is the piston sides where you are attaching it to the pin where you are having attached to the piston, right? This one, this is the piston. So here you are having pin. So here you are having the connecting rod, right? This way. And then down there you are having the crankshaft. So over here, where you are connecting this pin over here, basically piston pin, you don't have sufficient space. So to accommodate that, the only option that we are going to have is the needle roller bearings, because space is less and loads will be very heavy because significant load is going to be over there. So it means because of the combustion taking place, so therefore the most suitable bearing in case of a heavy duty diesel engines is the needle roller bearing, right? So that you can get, this is the needle roller bearings which is shown to over here. So these are some of the applications of the needle roller bearings where space is less, loads are heavy. For example, one application is, the other one is that oscillating motion that we had in the particular that rocker arm. There also we make use of this. Go through this. In a ball bearing, the ball is subjected to what? In a ball bearing, the ball is subjected to what? What kind of stress? Okay, you have to keep it in mind that in ball bearing, ball is subjected to what? The whole system is rotating, right? Let's say this is fixed, right? This is fixed. Outer race is fixed. So this is rotating, inner race is rotating. So when inner race is rotating along with shaft, because shaft, it is fixed to shaft. Let's say it is fixed to shaft. So not only shaft, when shaft is rotating, then obviously this will also rotate. Along with this, these will also rotate. Balls will also be rotating. And since you are applying a load through this particular shaft, then definitely what is going to happen? See, compressive stress is acting, that is okay. Compressive stress is acting, that is okay. But what should be the most appropriate answer? In such questions, you have to give the most appropriate one. Definitely, let's say when you're applying the load, the balls are getting compressed, but at the same time, you know, balls are rotating. So in one cycle, this point came into contact, and when after getting rotated, again, maybe not this point, another point may be coming in contact over here. So this is the rotational motion. So this is subjecting to fatigue loading, cyclic loading, right? So the most appropriate answer is going to be this one, right? So obviously this is also correct, but I have to find out the most appropriate answer. The most appropriate is going to be cyclic stress. Ball bearings are usually made from. Can you try to answer this? Try to answer. See, low carbon steel, high carbon steel, medium carbon steel, high speed steel. High speed steel, you normally make use of this steel in tools because you are adding alloying elements, and therefore cost is overall is going to be high. So this is not the, we are using this over here. Now you are left out with three options of low carbon, high carbon. So this idea you have to get from the point that if the carbon percentage is low, relative strength will be less. If carbon percentage go on increasing, strength go on increasing. At the same time, brittleness also increases, right? So for me, most of the application that I desire is that, okay, they have significant strength also, and but at the same time it should not be brittle, right? So if you will go with high carbon steel, the problem is with the high carbon steel is that you're going to have a high strength, but at the same time brittleness will also increase. So I will not go for that. Why I will not go for low carbon steel? Because strength will not be sufficient for me. So the most appropriate out of this is going to the medium carbon steel, where I'm going to have a combination where you're going to have a sufficient strength also, toughness also that I will get over there, and that's all, right? So that is what I want. So it is going to be the medium carbon steel. Give the answer for this question. Spherical roller bearings are normally used. What is going to be the correct answer? I think this question we have already addressed, isn't it? See, it was the same. It is the same question, only difference being the way it is asked. Spherical roller bearings are used for to compensate for the angular misalignments. It can adjust the that angular misalignment. For example, shaft, if there is possibility where shaft can little go this way, misalign, so they will adjust accordingly, right, to compensate for the angular misalignment. Compensate means what? Let's say there is a situation where shaft can go this way a little bit. So in that case, which is going to be the best bearing? So that best bearing could be the which can allow its rotation small way this way. That means angular misalignment. The same thing. This could be single roller also or double roller also. Double roller, high load carrying capacity. Single roller, little low. That is the meaning of this. If the load on the ball bearing is reduced to half, the life of the ball bearing will. If the load on the ball bearing is reduced to half, the life of the ball bearing will. What is going to happen? Go ahead. Have we done this? So if we reduce the load, this is one way of doing it. It is the same way like we did. So dynamic load carrying capacity is going to remain same. Dynamic load carrying capacity is going to remain same. So what is going to happen when we are changing the load? We said that is the same thing. L1 by L2 will be equal to It's the same line. HAL के इसी line पे रहेंगे same. It's not different. Okay. You are talking about difficulty level. So difficulty level, you know, it's a moderate only always in case of PSUs. So it's the same thing. Either you do this way or you can say L1 by L2 is equal to what? P2 by P1. And if it is a ball bearing, then 3. That's all. So accordingly, you can just get it done. So similar question we have already done. So I'm not going to solve it. Just go through this. Just go through this question. In hydrostatic bearing, the static friction is. Okay, go ahead. Try to answer. In hydrostatic bearing, the starting friction is what? In hydrodynamic bearing, you already know, right? In hydrodynamic bearing, you know the variation of friction. In which case? This is the case in, this is the coefficient of friction. So with the speed, you know the variation of coefficient of friction in case of hydrodynamic. But in case of hydrostatic bearing, what is, if in speed increases, what is going to be the coefficient of friction? Okay, one part is that, and the other part is that he's saying starting friction. What do you think? Very low, more, either more or less? So when the speed is low, in case of hydrodynamic, you know, friction is more. When the speed is low, friction is more. Over here, speed is low, friction is more. Hydrodynamic. What about the hydrostatic? Starting friction, initial. Hydrostatic, you know, we supply the lubricant from externally by making use of a pump at high pressure. So it means initially there is no metal to metal contact. So when there is no metal to metal contact initially, because from the very beginning I am just lifting it. First, before starting, before running the shaft, I am applying the oil at lubricant at high pressure. So I am separating the shaft at the very beginning. So if I am separating it, there is no metal to metal contact. So there is no metal to metal contact, it is going to be the very low friction, because only friction that will be present will be between the shaft and the lubricant. Okay, this question I will do when I will be doing, even though we can do it, but anyway, we will do it when I will discuss with you the clutch portion. So I'm leaving it because he has related it with the clutch. Okay, go ahead with this. Which of the following bearings are most stable for supporting high axial thrust? Okay, this is going to check your understanding. Which of the following bearings are most suitable for supporting high axial thrust? Okay, let me ask one question to you. Ball bearings, can they carry high axial thrust or a high axial load? You will say no, because they can carry moderate. Can roller bearings carry the thrust load? Roller bearings cannot carry the thrust load. They can carry very high radial load, but they cannot carry thrust load. I think it is not over there, but if you see the configuration of this roller, let's say I'm showing the half cross section. So this is the outer ring, and this is the, sorry, this one is inner ring, and this is a roller. Now think of situation, I have produced the recess or this raceway this way. So any load, when you are applying a load over here, axial load, So along with the shaft, this ring, inner ring will shift. When it will shift, then obviously this is fixed. This part is fixed. Outer ring is fixed. So it will try to interfere with this portion over here. Edges will try to interfere. No, even single roller. Why double roller? Single roller. I'm giving you a single roller. Because see this portion that you are having, at the end I am supporting it. So when I am applying any load over here, it is going to have the impact over here. So it is going to rub against that portion. And therefore it is going to create a lot of noise. Obviously rubbing action, and it will damage that. So axial load it cannot carry. But if I talk about this, why balls were able to carry the axial thrust? Because race is little curvy over there. So when I will apply the load, ball can shift a little. But if you apply very high axial load, then ball will shift to the extreme and therefore try to damage that edge. But yes, if it is moderate, it can little shift ball because it is circular, so it can just shift. Spherical, so it can shift. So it is not going to damage because you are having that surface that way. Raceway is having larger curvature compared to that ball. So it can adjust. But in this case, there is no possibility of adjusting. It will immediately start creating the noise and all that. So that is why whether it is a needle roller bearing or whether it is a cylindrical roller bearing, so all of them cannot carry thrust load. So thrust load capacity very low. Radial ball bearings can carry moderate, not high. This. Why? But keep it in mind, they are used in pairs. It will depend upon the situation. For example, if I want to carry the thrust load in one direction, so they can carry, okay, if I am having only a single tapered roller bearing, for example, over here, single tapered roller bearing, then single tapered roller bearing can carry the axial thrust in one direction only. Just see, I have a situation over here. For example, this is a roller, this is the same thing, and this external race is shown to you over here. Let's say if I apply axial load in this direction. Now, obviously, one ring will be fixed, so outer ring is fixed. When I will apply the load, this load will get transmitted this way. No issue. You're applying exerting load will be transmitted this way. So it can carry this load when you're applying the axial load in this direction. What if I apply axial load this way? This is a shaft. So in the shaft, you're having this kind of such a situation, let us say. So if I apply a load this way, can this bearing carry this load? This bearing will not be able to carry this load. Why? With shaft, you have fixed this inner ring is fixed on the shaft. So when you will apply the load this way, this ring will try to shift in this direction. If you will try to shift in this direction, you are generating the gap over here. So where is going to this load? How you are going to transmit that load? You are rather moving it away from this. Fixed is this. So it means for this configuration, only option you are having is you can apply load this way. So that means tapered roller bearings can carry axial thrust, high axial thrust in one direction only, not in both the directions. So if you want to carry the load in both the directions, then what you have to do? You have to use them back to back. For example, if you see over here, this arrangement is back to back. So let's say this is a gear which you have attached, and let's say you are having a load which is acting this way. Think of a situation this way. Which bearing out of these two can carry this load? Will this bearing be able to carry this load? Because inner ring is fixed to this shaft. No, this bearing will not be able to carry this load. Why? Because inner ring will be shifted. This is shifted, inner ring is shifted, so gap will be created over here. Think of this situation. Load is getting transmitted from here to here. That means from inner ring to outer ring. So this load, it can carry. Had it been this way, which bearing can carry this load? Inner ring transmitting load this way. And over here, this load trying to separate the inner ring, moving this inner ring in this direction. So it means creating the gap over here. So this bearing will not be able to. So combine together. So if we have the application where you are having the axial thrust in one direction only, go for one this tapered roller bearing. But if you know that okay, it is going to be in both direction, then go for the two tapered roller bearings back to back. As simple as that. You could have example, for example, you are having train coaches. There you can have, because in that case axial thrust is going to, because as that train may go this way, so maybe that radial load, thrust load may be acting this way. That means centrifugal load, because centrifugal force will act. So as train is moving in this direction, so one direction is this. Let's say if it is rotating this way, is moving this way, track is this way, load will be acting this way. So you have to carry in both directions. So in that case, you can go for back-to-back arrangement. This is how you have to understand. So I think you got it. Okay, I think we'll stop now. So these are some of the, I think, from the brakes and clutches that we will be discussing in some another lecture. So I think that is all for today. So I think we covered 2-3 topics today, like gear design, and then we covered shaft design and the bearings, right? So these are some of the questions, I think, in a holistic way, they are going to help you out. So in different areas. So that is all for today. See you in the next session. Till then, bye. Thank you.